Questions about anything? I always start out that way. So last time I just gave you an introduction to why I was so excited about the subject, and now we're going to get back down to earth and start following the textbook carefully. Today's lecture is about math induction, which is, for me, just pure fun. There's not a math induction problem that's not fun. So I'll do some examples and tell you some philosophies. I do think our textbook is very well written, and it's very math booky. You know, it has theorem proof, theorem proof. And I told you I had a class back at Michigan. The professor's name was U.C. Weissela. Had a mind-blowing name with 3 A's with double dots. A Finnish guy visiting University of Michigan doing research with the chairman in the department. And I was really fired up about his class and really enjoyed it. And I would carefully write down everything he said in class and then go home at night and write it in this notebook, clean and perfect. And so basically he gave me a book on the subject. And I thought, oh, I'd like to use this when I teach it. But then I realized I loved this class and wrote down every word he said, but I realized I couldn't stand it now because it would just be like writing a book or copying a book. And I don't want to teach that way. So I've kind of freaked out that I said, I'm not going to do it this way, even though I thought it was wonderful at the time. I want my lectures, what? What the? Oh, crap. Okay, my wires are loose. That could explain a lot. What the heck? My screen up here is flashing on and off. This is usually a bad sign. Okay, well, I'm back in business. Okay, so I want my lectures to be stimulating, more stimulating than that, and I want them to prepare you to read the book carefully. It's going to be important to read the book because the book says everything, and the book, does theorem proof, and I wanted my lectures to prepare you to read that. And of course, I'll cover the main topics, but I'm not going to cover every topic in quite so pedantic a way. So that's my philosophy, and I'm going to start doing that. So were there no questions about anything? There's homework assignments on the homepage, and it's due next Wednesday. Okay, so I thought I'd start out with math induction with everybody's favorite problem they probably have seen somewhere before, just because the details aren't difficult. Let's do the classic example that 1 plus 2 plus blah, blah, blah out to n is n times n plus 1 over 2. And the principle of math, so this is a statement about a natural number n. If you add up all the numbers from 1 to n, the sum is going to be something simple like that. Okay, so this is I would call this thing P sub n. It's a statement about that real number n. This statement. An integer n. Okay, and the principle of math induction goes like this. Suppose we know that P of 1 is true. Let's see, we do know that P of 1 is true. P of 1 is true. Duh, because, let's see, P of 1 is, let's see, the number is 1, and that's equal to 1 times 1 plus 1. I'm putting the red thing where the n would go, over 2. Check. Duh. Okay, so P1 of true is true. And now the principle of math induction is that, well, if we can deduce the next statement from the previous truth of the statement, then we can deduce that they're all true for all n. So we suppose we know that P for some number n is true. Then we can deduce somehow, so we know if we can deduce the statement for the next one from P sub n, then the statement is true for all n. What is happening? That's the principle of mathematical induction. Okay, let's see if we can do that. This is called the principle of math induction. Mathematical induction. And I'll call that PMI. So I don't have to write it again. Okay, let's check if we can do that for this case. Here's what P sub n is. It's 1 plus 2 plus blah, 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 3, etc., out to n is equal to n times n plus 1 over 2. Okay, so we assume this is true. Does my red look red? Kind of. So we assume we know this. Then we got to figure out if it's true for the next one. So what would the next one be? The next one would be n plus 1. That would be 1 plus 2 plus blah, blah, blah. It would go out to n, but it would keep going. And this time I'll put my n plus 1 here. And we got to figure out that that's equal to what that formula would spit out, namely n plus 1 times n plus 1 plus 1 over 2. Okay. We know that this thing from the previous step is equal to n times n plus 1 over 2. Okay. And therefore we can start messing around with some algebra and see if we can write this in the form that we want. Namely, n plus 1 times n plus 1 plus 1 over 2. That's what we want to show this thing is equal to. Well, let's see. How do you do that? That would be n times n plus 1 over 2. And then to put them both over 2, I'll put a 2 times n plus 1 here. Over 2. And let's mess around with that. Let's see, can I, n times, I can factor out an n plus 1 in that top thing and have n plus 1 times, there's an n and there's a 2. And that's the aha moment is that n right there, I can write as n plus 1 minus 1 equals n. And so now when I look at that, that formula becomes, I'll make it the number in red, n plus 1 times n plus 1 plus 1 over 2. And check. That means the formula is true when I stick n plus 1 in the formula. Okay, so the induction step is true, and that means that this thing, let's see, why do you believe the principle of mathematical induction? Everybody believes it because, here's why we will believe the principle of mathematical induction. P of 1 is true. Check. The induction statement means that if I know it for P of 1, I know it for P of 2. Check. And now I know it for P of 2, so the induction hypothesis means I can deduce it for P of 3. Check. Etc. And so everybody believes that shows that it's true for all n. Everybody believe it? Way back, various people, Peano, for example, wanted to write down sort of axioms for the integers, just like there's axioms for geometry. And so it was always, the beginning of the axioms were always kind of trivial, like commutative property, distributive property, the kind of stuff that's really boring to read in a book. But then the most interesting, you needed something like the principle of math induction. And so the last fanciest Peano postulate is the principle of mathematical induction. And it's a fun thing to do, to sort of treat the theory of natural numbers like geometry and have postulates and theorems and write it all out. Richard Dedekind did it also at a later date in a clean, nice way. And I'll talk a little bit more about Richard Dedekind when we come around to thinking about what the heck are the real numbers. We have to convince ourselves we know what the natural numbers are before we can start thinking about the real numbers. And that's kind of why we're starting at this elementary point here. Let's see, I think I'll do another example. Some of the homework problems are kind of fun, and I wanted to get you ready to do them. Let's do, I guess there's no point in changing colors here today. I'll stick with black. Another fun problem. Let's see, this is kind of an easy one. Show that n is less than 2 to the n for all n. That's easy to believe. Let's check for n equal 1. Is 1 less than 2 to the 1? Check, yes. So it's true for n equal 1. Now for the induction hypothesis. Suppose we know it's true for n. Let's see. So suppose we know it's true. I like to use a capital N here, just because it sticks out more, which means that we know that n is less than 2 to the n plus 1. We need to deduce that it's true for the next one. So we need to deduce yeah, thanks. Sometimes I say one thing and write a different thing and think a third thing. So I appreciate when you catch me doing that. What we need to deduce is that n plus 1 is less than 2 to the n plus 1, not from scratch, but from this previous one. Okay, let's see how we do that. So you think about, okay, you start with that left-hand side. Let's see, n plus 1 is the left-hand side. And let's see, I know from the previous thing that n is less than 2 to the n. So this would be less than 2 to the n plus 1. And is 2 to the n plus 1 less than 2 to the n plus 1? Think about that for a minute. I kind of wish I had another 2 on that line that I could what should I do? What? You would be proving it without using math induction, probably. I want to do a lazy way of doing it where I don't have to know what the log is.
You say that's less than 2 to the n plus 2 to the n?
Yes! Okay, so I want to use something that's sort of basic and easy, just using inequalities. And the key here is that, well, 1, I'd like to say it's less than 2 to the n, but at the n equals 0 case, it would be equal to 1. So 1 is less than or equal to 2 to the n. But I have a less than right here. So a less than or equal to sign is going to allow me to say, so n plus 1 is strictly less than 2 to the n plus 2 to the n, which is 2 times 2 to the n, which is 2 to the n plus 1. Check. Okay. Stuff like that. So you've got some homework where you have to do stuff like that, playing around with inequalities. I think they're fun. You might get puzzled at some point, but playing around a little bit, thinking about what you need and going backwards sometimes help. Questions about anything? Yeah.
Do we have to state that n is within natural numbers?
Well, that kind of goes without saying when you're doing math induction. Yeah, so n are the natural numbers, 1, 2, 3, 4, etc. And the first inductions, you have to know that p of 1 is true. And so, yeah, it starts with the natural numbers. It's for natural numbers only. I guess I want to get you another example similar to a homework problem, just so you see what they're like. I want to show that 5 to the 2n minus 1 is divisible by 8. For all n. So instead of saying for all n, I'll say for n in the natural numbers. Okay, well, let's think of the first case, n equals 0 case. N equal 1 case, rather. That would be 5 to the 2 times 1 minus 1. That'd be 25 minus 1 is 24. Definitely divisible by 8. Check. So the P of 1 statement is true. And now we do the induction hypothesis. Suppose we know it for n. The P of n is true. Namely, we know that 5 to the 2n minus 1 is divisible by 8. Oh. Okay. I want to deduce that the next one's divisible by 8. So we want to see, let's see, what would Pn plus 1 be? Pn plus 1 would be 5 to the 2 times n plus 1 minus 1 is divisible by 8. And that's a big question mark. We don't know that yet. And I don't want to deduce it from first principles. I want to deduce it from the previous one. So that's really what I'm trying to use. So what should I do? Any ideas? Yeah.
You try and get 5 to the 2 n minus 1 divisible by 8, and if the difference between 5 to the 2 times divisible minus 1 and 5 to the 2 n minus 1 is also divisible by 8, then 5 to the 2 n times divisible by 8 must be divisible by 8.
I believe that would work. But it's a tongue twister. I'm amazed you said it. I don't know. I feel lazier than that. I just want to write 5 to the 2n somehow. Because I have a formula for 5 to the 2n above. And so it's basically what he said. I'm going to do it sort of backwards, though. This thing right here, let's see, that would be 5 to the 2n plus 2, which is equal to 25 times 5 to the 2n. And so the whole thing now is going to be equal to 25 times 5 to the 2n minus 1. What should I do next? If I'm like, yeah.
You separate the 25 into 24 and 1.
Yeah. Okay, that's going to work too. That's exactly what I should do. Well, I wish I had. Now I've got a 5 to the 2n. That's making me feel pretty happy. But I need a minus 1. Okay. And so actually, I'm going to do it this way. What does purple look like? Minus 1. It doesn't look like anything, does it? Huh. Okay, I'm going to fix that next time. And I'm going to add. I'm going to give myself what I want, but then I have to add it back. Now I'm getting somewhere because I know 5 to the 2n minus 1. I know that's divisible by 8. And now when I distribute that 25 through there, I would get, let's see, 25 times 5 to the 2n minus 1. And then I get 25 times 1 minus 1. That would be plus 24, which is what you did in your head. And it's basically what you told me to do also. And of course, I know that this one's divisible by 8, and 24 was divisible by 8 because that was the first step. And so the whole thing is divisible by 8. This one's divisible by 8. Means I could factor an 8 out. And so when I factor an 8 out of both of them, I could pull it in front by the distributive law. And so check. The whole thing is divisible by 8. So that's how you do those problems. It's some messing around and playing around. The thing is to isolate the piece of n formula somehow and use it in the next formula. And sometimes if you can't figure out how to do it, you can start with this and go backwards. Questions about anything? I guess we're starting out slow. You probably have seen stuff like this. high school or junior high. I want to give you a hint for one of the problems, because it seems frightening at first. A hint for section 1.2, number 10. They don't tell you what the formula you want to figure out is. And so you think, oh my gosh, how am I going to guess it? It would not be advisable just to write down instances of 1, 2, 3, 4 and see if you recognize a pattern. That would be a long shot. This one is important to think about. So this problem, you're supposed to figure out a formula for the sum. By the way, when you figure out the formula for the sum, you certainly don't need math induction anymore. But they ask you to verify the formula via math induction. Let's see, so those are the odd numbers. And notice the second one repeats. And so the general term in this thing is going to be previous odd number times the next odd number. So what the heck is that going to be equal to? Something clean or something horrific? Any ideas about what I should do to get this going? Yeah.
You can split it up. Just partial fraction.
That's a brilliant idea, yeah. This thing, I'm thinking, when I see this, partial fractions. And so let's see what partial fractions would look like. An a over 2n minus 1 plus a b over 2n plus 1. And you could do the partial fractions, treat the n like an x, and do partial fractions from freshman calculus, and you would find that the a and the b are plus a half and minus a half. Yeah, so when you, oops, plus 1. Okay. Now what? Yeah.
Pluses and the minuses.
Exactly. That's what you would call the telescoping series back in Math 162 or someplace. Okay, so when we start writing out the sum there, we'd get, let's see, the smaller one minus the bigger one. So it would be 1/2 times 1 over 1 times 3 would be 1 over 1 minus 1 over 3. And the next one would be the smaller one, which is 1 over 3 minus 1 over the bigger one. The next one, et cetera, et cetera. And then the last one would be 1 over 2n minus 1 minus 1 over 2n plus 1. And the word, we realize there's going to be pairwise cancellations of all the middle terms. The 3s, the 5s, etc. This one, the only thing that's going to hang out is the last one and the first one. And so there was a word for that back in freshman calculus. This is a telescoping series. And you get a rather simple formula for that thing. And then the homework problem is to verify it via math induction. Which is kind of dumb, because now you proved it from first principles, but the homework is to verify it using the principle of math induction. Every book on the subject would tell you there's various things that can go wrong with math induction and sort of subtle mistakes you can make. My favorite example of such a thing is all cows are the same color. Certainly, if you only had one cow, it's only one color. That cow would be the same color. So P of 1 is true. And suppose we know P of n is true. If there's n cows. We're assuming there's only finitely many cows. Suppose P of n is true. Then I want to think about, what if I had n plus 1 cows? Well, I stick all my cows in a field and I yank one out. Then I would know that then I would have n cows, and they'd all be the same color. Okay? Then I stick the cow that I yanked out back in and yank out a different one. All those cows would be the same color, which means the cow I yanked out was the same color as all the other cows. So, of course it's true. Why is this defective reasoning? Yeah. Yes.
Oh, if the one he pulled out was a different color,
Yeah.
it wouldn't not go through.
Well, then I stick it back in and pull out a different one. Yeah.
Like pulling cows out doesn't actually relate to the empathizer. It's just
It's true. This is kind of a sneaky problem because it's so ridiculous. Yeah.
Because it's only related to your specific sample size, but not all cows.
Well, my sample is all cows. I could say cows in North America, but it's all cows in the world. Yeah.
This doesn't hold for when n is 1. Like if you,
I mean, I think you're on the right track. If there's only one cow, what does the word same color mean? It's all cows is that one cow, and it's purple.
like the recursive part. When
Exactly. Oh, yes, right. It's going from P of 1 to P of 2 that breaks down. And if that breaks down, the whole thing breaks down. So, meaning if I have 2 cows, I take one out, and of course I only have one left, it's the same color, then I stick it back in and pull out the other one. My induction step was very much based on the fact that I would have a color when I take one out. So the P of 1 to P of 2 fails. So the mistake in this example is that P of 1 does not imply P of 2. All the other ones do. But if you don't have that one, you're sunk. So you got to be careful sometimes. You got to make sure that you don't flub up somehow and realize there's a special case early on. And the book gives you a couple more examples of where, it's a sneaky mistake you could make if you're not careful. So the PMI crashes at the first stage. I mentioned the piano postulates. which are kind of fun to look at in a book. The last one is the PMI, Principle of Mathematical Induction. It's kind of like in Euclid and geometry, trying to figure out what are the axioms. You know, there's the parallel postulate. And everybody went ape for centuries trying to show that you didn't need the parallel postulate. Or maybe, and some people discovered you could throw it out and you still have that, axioms for something, mainly non-Euclidean geometry. And so a question you might ask is, could there be different postulate, a different axiom? The principle of math induction is basically an axiom for the theory of number theory. And the question is, well, is there a simpler, more natural axiom to put in its place? And one that works is called the well-ordering property of the natural numbers. Property of the natural numbers. I'm going to call that WOP today. And it says this: every non-empty subset of the natural numbers has a least element, the smallest one. This can be used in place of the principle of math induction. So what I want to show you today, this is sort of a good exercise for learning how to write down rigorous arguments, which is what this course is all about. We're going to write down rigorous arguments about functions of a real variable. This week we're starting out with integers, which are somewhat easier to think about. So what I claim is that this could be a better axiom maybe than the principle of math induction. So my claim is well-ordering property implies the principle of math induction. And of course everybody believes the well-ordering property of the natural numbers. Let's see. I want to explain why that's true. Well, let's think about it. Okay, so let's suppose we have a statement about natural numbers, like we've been playing around with. Okay, and suppose we know that P of 1 is true. And we know that if P sub n is true, then the next one's true. What? We know that if P of n true, sorry, I'm getting myself messed up here. Know that if P of n is true, then the next one is true. But we don't know the principle of math induction. We're going to assume we know the well-ordering property. So we know the well-ordering property but we don't know the principle of math induction. We want to deduce the principle of math induction. Okay, so somehow I've got to get a non-empty set of numbers and play around with the well-ordering property. Okay, so what should the S be? Should it be the set of integers that makes this thing true? Let's think about that. Let S be the set of n such that p sub n is true. If the principle of math induction is valid, which is this stuff here, we want to see that S is all natural numbers. S is equal to n. Well, suppose it isn't. And let's see. S is not the whole natural numbers. Then the book likes to use set minus. It uses a backward slash. So n minus S is non-empty. And so the well-ordering property implies that there be a least element in there. Gives a least element. N naught and n minus S. Why is that? I want to get a contradiction here, so that my supposition here has got to be wrong. If I get a contradiction, then it was not true that S is not equal to n. What is wrong with that? It's a least element. Well, 1 is in S. Well, I'm thinking out loud now. 1 is in S. Because it's true for 1, we know that. So the least one is not, n naught, the least one, is not equal to 1. Okay, and it's the least one. And so n naught minus 1 is an integer, a positive integer, or it's a positive integer. So it's not equal to 1, so it's greater than 1. And it's the least one. And n minus 1 is less than n naught. And n naught is the least one. The least one in n minus S. And so we have to conclude that this thing is in S. Why is that weird and disturbing?
Define as an element of the
Yeah. Right. That's going to be a kind of a contradiction. The key at this moment is the induction hypothesis. If it's in S, it's true. And we know the induction hypothesis, that if it's true for that number, it's true for the next one. The next one is going to be n naught. And that's the least one for which it's not true. There's the contradiction. So the aha moment is that the induction hypothesis yields, let's see what, P of n naught minus 1 implies the next one, P of n naught. But it's not in the set of true, where it's true, it's in the complement. And so that I learned this symbol in UC Weissela's class. That's a contradiction. So that symbol for me means contradiction. For everybody, in fact. A lightning bolt. And so where did I go wrong? When I assumed that S was not all of the natural numbers, it led to this contradiction. So S is all of the natural numbers. So assumption that S unequal to n must have been wrong. So S has to equal n. And that's what we wanted to see. Check. Questions about that? That's kind of a hard thing to swallow. I mean, it's the kind of thing you have to sit down and write out yourself just so you convince yourself you believe it. But it's kind of a nice little thing to think about. Oh, let's see. I've got a couple of minutes here. I didn't talk about section 1.1 because I couldn't face it. But there were some words from section 1.1 that I should mention. Some of the words are injective. It's the French word for one-to-one. And surjective. If you want to say cool, if you want to sound cool, you can say it with a French accent. Like surjective is the French word for onto. There's some subjects where the French sort of started it and the word stuck. Whereas when Richard Dedekind took over, he used the German versions of those words, which didn't stick. And bijective, or bijection. Bijective is one-to-one and onto. But being from the Midwest, I prefer the short one-to-one and onto words. And so every now and then I'll slip back and forth between these two. And also I mentioned that the A minus B, that's equal to the set of X, such that X is in A, and X is not in B. So if they don't intersect, then of course you're not taking anything away. So that you're only taking away when they intersect. The book calls that the relative complement. Some books make this exactly the same as A minus B, or some use that symbol. That's the same thing. Anyway, I'll try to stick with the book's notation, but I might slip every now and write A minus B instead of A backslash B. Any last minute questions about anything? Okay. That's enough for today. By the way, the homework will be turned in Gradescope. So I've hooked up the Gradescope to the Bytespace page.